It'll be fun regardless. All right. Stat edit. Okay, so let's do the guys in, since I called mu1 the guys. We'll just get, let's just give me inches. So instead of feet and inches, just give me inches. Go for it, Michael. How tall? Or tell me feet and inches and we'll convert. Tell me feet and inches and we'll convert. Yes. It's 9 o'clock in the morning. Expect me to convert? Just give me your height. 6.
It's going to be 70 inches.
70 inches. There we go. There we go. 70. Sorry, Mr. Harrison.
75.
75. There we go. Will.
69.
There we go. Jack. 70. Excellent. Jess.
5'4".
5'4", so 64. Eric.
69, I think.
69, yeah. Eric.
70.
70. John.
Yeah, 70.
70. Chris.
71.
71. Who walked out? This is.
Oh,
Can I envision you sitting right there?
with beard.
Oh, it's Drew. We'll get him when he comes back in. Okay. So now I'm over to L2. We'll get Drew. Maybe we have to add Drew back in. Or I can freak him out and go to the bathroom and, dude, how tall are you? And then get fired.
Just walking. 73, all right.
Exactly. Hang on. I shouldn't be
He's trying to
talking.
measure himself.
That's what
He is.
we have a roller in the bathroom? It's kind of disturbing. Rosie, how tall? 5'9", so 69? 69? 5 times 12, 69, yeah. All right, good. Tina?
5'3".
So that's 63? I think I'm doing this right.
65.
65, there we go. Laura?
68.
68. Beautiful. Ash?
71.
71. Rachel?
63.
63.
Any shorts?
That's okay. That's shorties. It's all based on a bell curve. It's funny, I posted a picture yesterday. I try to always wear a Punk Bands t-shirt when I'm doing the videos and then put it on Facebook with a link to the bands, and the bands get some. And I was wearing a Creep Records t-shirt, and up behind me was a bell curve, and every Creep Records band was like, they sent me these Facebook messages. What the hell is that curve behind you? Why are you wearing our t-shirt and putting it in front of mathematics? And half of them were pissed and half of them were stoked. It was kind of fun, actually. What do you got, Danny?
66.
66. Kels. 62. Kels. 70. All right. And we'll get Drew when he comes back. Let me get this focused better. Everybody got that L3 is irrelevant. That's left over from a goodness and fit test. That's just irrelevant. I'm going to clear that out either. So let's make sure we go through it again. There's the guys and girls. Perfect. Now, FYI, again, this is outside of the scope. Yay! Kaylee, how tall are you?
Hey, I'm 5'5".
5'5", that's 65.
Yeah.
Perfect.
Sorry I'm late.
Don't worry about it. You're not late, you gave us data.
Sweet.
Now, technically, what kind of tests are we going to run, folks? What kind of tests are we going to run? Go ahead, be brave. It's T's. It's a T test because you're testing the average height of guys and the average height of girls. So technically speaking, since it's a t-test, and since we have teeny tiny samples, think back to your last project. When you got teeny tiny samples, you have quite a bit of variability in them potentially. So you should, and this is not saying I'm not going to ask you to do this on Thursday, but I'm teaching now for beyond the class when you're actually sitting and doing research on your own. This data should look-ish like bell curve data. It should look roughly normal. Okay, I'll test it just to see what the hell, why not? But here's the guys. Oops, one. And here's the girls. I'll do the girls with that so it stands out.
And we still have Drew.
Oops. We'll get Drew in a second. Why is it saying syntax? All right. Oh, shiza, hang on. Oh, L1, I thought I changed that to 1. I didn't change that to 1 either. I thought I did. Enter. Oh, I see the problem. I see the problem. I see the problem. Go to. Change it to L2 for L1 for a second. I see the problem. It doesn't want me to do that, so I guess I have to make 2 histograms. That's kind of annoying. All right. Well, I will then. Now this is gonna suck. That's okay. Oh.
You got way too much going on with that calculator.
No. It's just the TI is a pain in the ass for doing this kind of stuff. Okay, it's kind of hard to see. The guys were here, here, and here. That's believably a bell shape. The girls are here. They were the 3 bars coming across. That might not be as believable, but here's what I would then do. I would then go back, I'd turn off plot 1 and just resume the data. There's the girls, and I might mess with it a little bit to try to see if I can pull a bell out of it. It might be very hard to do that. So here's where one of those things you might have to then take the data and do something like you did in project number 3, which is bootstrapping. Assuming that you've got a good sample of whatever we have, 9 data points. Then create a bootstrapped data set that's larger to create an actual, Lindsay, how tall are you?
I am 5'6".
5'6", 66 on L2. She might have tipped it over to bell shape, I don't know. Anyway, the point being is that if the data doesn't look roughly bell shaped, you might not want to crunch data in this way. But we're gonna forge ahead. We're gonna forge ahead regardless. Does it look like the guys are taller than the girls? Let me turn a different plot on for you. I'm going to turn box plots on. Okay, here we go. Oh, I turned it off, that's right. Okay, guys up top, girls on the bottom. Doesn't look like the guys are taller. It kind of does. I mean, even with an outlier on the low side, I mean, look, this is kind of slick actually. The Q1 on guys is the same as Q3 on girls. So in other words, 75% of guys in the room are taller than 75% of girls in the room. That looks like they're taller, yeah? Now, of course, that could just be random noise, yes? That could just be random noise because we have small data sets, but don't worry about that. That's the kind of stuff you worry about in your junior and senior level stat classes, and it's super fun to worry about. Just try to teach. Drew, how tall are you? 5'11". Throw a 71 in there. Regraph. There. Oh, look. One of the whiskers disappeared. Fun. Thank you, Drew. That makes the data set even more ridiculous looking. Yeah, this is quite nice, yes. A box and whisker with no whiskers. You saw one of those back in 243. Thought I was making it up, didn't you? All right, so we can test it now. Now we just test it. We just see if it looks like they are. Now the question is, does the margin of error eat up any difference? I don't know. That's why we do these things. All right, we don't have stats, we have data. This is what Rosie was asking about before. Let's set the lists up. The lists are in L1 and L2, yes? Oops. L1, L2. Frequencies on these. Frequencies are just 1 because you're actually listing them in singletons. You're not grouping with a frequency distribution at all.
I told you to one and I keep being a Y.
Yeah, press the alpha button first. It's stuck in alpha mode. It's a glitch. TI never fixed. And then we just make sure we have the sign point in the right way because we are doing a one-tailed test. We're trying to see if the guys in U1 are taller than the girls in U2. So I need to switch this thing over to here. I think we're ready. Pull, leave it on. No reason to pull anything. And then we just do it. Because so tight. So if we have any area, it's going to be on the right because it's a right-tailed test. C. Nope, not a whole lot. Nope, not a whole lot. Almost exactly 3 standard deviations. You guys are amazing. Almost exactly 3 standard deviations above. Turn your plot off. Same thing I was getting. I had the damn wrong plot on. So, what do we think? Does it appear that guys are taller, or does it not appear that guys are taller? It was not.
Yeah.
Which one? Yes. I love hearing your voice. I don't hear it very often. It appears that guys, my math major, it appears that guys are taller. Yes. It appears that guys are taller. There's almost no chance they're not taller based on this data. Yes. There you go. This is a 2-sample t-test. So same thing, guys versus girls, just like the last one, but the last time we're looking at percentage of guys and a percentage of girls. Here we're looking at the average measure of guys and the average measure of girls. So there you go. How's that? Decent? Okay. That's my question, Dave.
Mine has that as sigma.
Oh, make sure you're running a t-test, not a z-test. It's a 2-sample t-test, yes? Yeah, that's the problem. That's why I told you guys, and this is weeks ago, you probably don't remember it. But I said, you're never going to run a z-test on this thing unless it also has the word what in it. Do you remember? Four-letter word, starts and ends with P. That's right, prop. Because if you try to run a z-test without the proportion, the prop, look what it asks you for. It sounds like that's what you ran, Danny, back there, yeah? The z-test, one of the first things it asks you for is sigma. You know what you tell it? Ugh. You don't know what sigma is. You never know what sigma is. You can't. And what they say is, well, assume sigma is the same from a previous study. Why would you do that? Why would you assume something is the same? It's like, I'm going to move to Bend from Delaware. I want to assume it's the same as Delaware. Why would you do that? Doesn't make it right now. It feels like it. But I mean, why make the assumption when you can actually test it using statistics? That's the whole point. Danny, make sense? Good. Good. You want to take 5? You want to just do a golf and be done with it? Do a golf, be done with it? Do a golf, take 5? Let's do Democratic. Want to test it? No. Do a golf, be done with it? I think I have a golf. I thought of a golf while you guys were crunching that last t-test. It's kind of stupid, but we're going to test a quarter of the year in which you were born. So January through March, April through June, July through August, September. Wait, I'm off. July through September, October through December. We're going to see if there's a difference in frequency of birthdays per quarter. This might sound stupid. The reason I thought of this might sound stupid, but this actually came up in the Vietnam draft. In the first Vietnam draft, which happened, I believe, in '69, I think, maybe '68, the first Vietnam draft, for some reason, drew more people from October, November, and December, more young men that had birthdays in October, November, December first. So in other words, if you were born in that draft year, in October, November, December, you actually had a higher chance of going into battle first, which means you had a higher chance of dying. Now the next 3 drafts, they changed the procedure and that disappeared. And it leads one to wonder, did they do something wrong the first time? And what's interesting is how they drew the draft was they put 365 balls in a bin, like the lottery. Literally, it was called a draft lottery. And they aired the balls up. No, they didn't. They didn't have the air machine. It was just the House of Representatives leader stuck his hand in and grabbed one. And then pulled it out and read the number and put it aside and shuffled them up. Yeah, right? Exactly. Exactly. But that was the deal. And the idea would be that it should be random if he's shuffling each time. But for some reason, they got a disproportionate number of October, November, December birthdays. So I started thinking about that, and the less depressing with you guys. Because we're not actually going to test and send you off to war. We're just going to test and see. So, assuming no preconceived notion, what do you think is going to be true about the frequency of birthdays in the first quarter of the year versus second quarter versus third versus fourth? Rosie!
Can you break down the sentence?
Oh, like actually say the sentence, I would say?
Yeah, just because that.
Sure! Absolutely. I like this. And I want you guys to think while I'm writing it, what question this is like that we did last week, or beginning of this week. So are birthdays uniformly distributed across the year? I might have a little bit more than that. That's the crux of the question. And then I have to give you data, which we're going to collect right now. So what I'm going to do is I'll make a little chart here. We'll collect our data together. We'll go January through March. We'll go April through June. Yeah. Is that right? April, May, June. Yeah. We'll go July through September. And then we'll go October through December. And now I know that's not perfectly distributed. My son and I had a long discussion last night after we finished reading before we went to bed about how many days each month had. He was very confused that February had 28. And I said, brother man, it confuses everybody. They used to think all the months had 30 days. I shouldn't say they used to think, they used to have all the months have 30 days. And then it started snowing in June. They said, we better fix something. So they started screwing with the dates. And I told them the knuckle thing, about how you know which months have 31 days. That was fascinating to him. We're all being 6, everything's fascinating. But then he was really confused, like, why does some have 30 and 31 and 28? I'm like, honestly, you've tapped the reserves of my knowledge about the calendar. And then he fell asleep, and I was like, thank God. Then he fell asleep, talking to Brian, so you find one. It's about the number 0 while you're at it. So, how many birthdays we got in January, February, March? 4. 4 of them. All right, how about April through June? 4. This is looking good. July through September. 1, 2, 3, 4, 5, 6, 7. And the rest, who haven't I counted? 1, 2, 3. Jack, just stretching, right?
No, I was.
Oh, you were here?
No.
No, you were here. Okay, so you were just stretching. Yeah. All right. Oh, we got another April? That's okay.
That's only
Don't
18.
apologize.
Oh.
Apologize. All good. There's our data. There's our data. It's fun. Fun, right? And there's an interesting tie to this. I was going to actually, if I could find this data set. Put that on your exam. I probably can't find it. I'll tell you about it later, though. And this again seems superfluous, but there is a neat tie back, besides just the Vietnam draft, which is becoming less and less meaningful every year as students get younger and younger, and I
We
get
don't
older.
only have 19.
So, Rosie, answer that question you're thinking of.
Well, isn't this the observed?
Yes, it is, and we have to set the data up that way. But in order to do that, you got to know what goes here, don't you?
Right.
So what goes here? What goes here? Right, and what does that mean? What does it mean for data to be uniformly distributed? If I pick a student at random, Chris, for example, probably random right next to me, but if I pick him randomly, what's the chance his birthday is going to be somewhere? If it's uniformly distributed, Dina, go.
Oh, just wondering, we have 21 people in here, but we only have 19.
That my favorite. It's okay.
Okay.
It's totally fine. I'll throw myself in to make it feel better.
Okay.
It's honestly, this is so seat of the pants. Really what we're doing here is we're looking for conclusions, but the idea is making sure you know what to do with the type of data that you have. That's okay. Totally fine. Totally fine. So the question remains is, what does it mean to be uniformly distributed? Say that again. Yes, any chance of being born in any one of the 4 quarters is going to be equal. So it's the iPod randomizer with 4 songs. We had 10 songs before, yes? I was going to do it by month, and I thought that might be kind of dumb. Because by month, there's so few of us, we're going to have a lot of zeros, which is okay, you can have zeros, but then it becomes even less likely to see anything because there's so much random noise. So by quarters, it makes it a little bit better. So yeah, the chance of being born from January to March is going to be the same as the chance of being born April to June. It should be the same as the chance of being born July to September. It's the same as the chance of being born October to December. It doesn't matter to me how you write it, as long as somewhere in there you indicate that the proportions are all equal. Laura, back to your awesome question from, I think it was either Tuesday or the previous Tuesday. This is one of the random tests. You can have a non-random test if they're not all the same, like the M&Ms. But this is one that actually is random. We're trying to see if everybody's fit neatly into the 4 quarters of the year. So it can test other than random, but this just happens to be one more random test. Cool? Awesome, awesome. What's the opposite?
One of them's
Good! One of them's different somewhere. Yep. They're not all equal. There might be, it looks like, looking at our data, it looked like there was a spike in July through September, but again, that spike is relative. Is it really a spike? Is it really a spike, or is it just the biggest we have? That might not be, it might be meaningless in that way. Oh, I'm actually glad I did that, so I made the math easier by adding myself in there. Okay. So, Rosie pointed out this is the observed expected. We have to make 2 columns. We have to make the column what we saw and what we should have seen, assuming this is true. And that's where the expected comes in.
So if it was true, then it would be equally.
Yes, and that's why I'm glad I threw myself in there, because 20 is an easy number to divide by 4. Yes. So here's the data. You have to set up the data this way. 2 columns. And all you got to do is 2 columns. You don't have to do any more than that. The TI does the rest as far as the crunching. You put your observations, 4, 6, 7, and 3. And then you put your expected observations, which would have each been 5.
5.
They should have all been 5, because if you spread 20 birthdays evenly across the year, there should be 5 in each category. Beautiful. And then we test that. Now the way I made you originally test it was by doing subtraction and squaring and division, and then we summed up everything and then we tried uncle. That's why I gave you the program. The program does all the work for you at this point. So let's swing around and run the program. Make sure you know how to run it. The first thing